assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
Hi there. So for this problem, we need to calculate the electric potential at a point P1 on the axis, and it is at a distance d from one of the end of a thin plastic rod that has a length of 12 centimeters and a non-uniform linear charge that depends on the position x. So the first thing that we can do is to consider an infinitesimal segment of the road located between in here. We can say that this is the infinitesimal segment. We can say that it is between the points x and x plus delta x, and it has a length of a differential dx. So this is dx. So and it contains an infinitesimal charge, so that we can write that this contains an infinitesimal charge of dq, which is the linear density lambda times dx. So we also know that the definition of the linear density is the total charge over the length of the rod. Its distance from P1, if we sum this, the distance from P1 to that infinitesimal point or segment should be d, which is this segment, plus x. So it should be d plus x. That's the distance to that segment. So the electric field created by that segment should be of the form that the differential and electric potential is 1 over 4 pi epsilon 0. That differential, that q, over the distance to that segment, which is d plus x. Now, in here, as I said, we can express that differential in charge as in terms of the linear density, so that we will have delta lambda times the differential in x over d plus x. Now, since we need the electric potential created by all of this rod, what we need to do is to integrate, because with that we will consider the contributions of all of the segments from one of the end of the rod to the other end of the rod. So to do that, so integrated, we have that the total electric potential is the integral from 0 to L. That's the length of the rod, and we integrate what we found in here. Also remember that the for this problem we are given that the linear density has a dependence on the position, and it is equal to c times x. So we're gonna put that in here, 1 over pi 0 c times x dx over d plus x. And here we can see that we can take out all of the constants. C for pi epsilon 0, and we are given with we are left with this integral. And we need a way to solve this. So I'm gonna do some trick to make this easier to solve. We can see that if I add and subtract d in the numerator, just like this, I add d but also subtract it. It is like I have add a 0, so it doesn't affect the integral. So this over this. So we can see in here that I can divide this part by this, and I will have c over 4 pi epsilon 0. So we'll have 0 else of that, which is just the integral dx, and the other one it's gonna be minus 0 from L of d over d plus x times dx. Of course, all of this is multiplied by that term. In doing this, we are left with two more easy integrals. The first one is just x. The integral of dx is just x. And for the second one, we can see that d is a constant that we can take out of the integral. So we are left with an integral of the 4 dx over x. We don't care that much for the plus d, because that comes into the argument of the integral of that function. So it will be c over 4 pi epsilon 0. So as I said, the first one is x. Remember that we need to evaluate this from 0 to L, and the other one should be d, because we can take out that of the integral, and will be the Neperian logarithm. That's the integral of a function of 1 over x. And in this case is d plus x, because that's what we have in the numerator. Of course, we can do this because there is no constant or other thing in front of the x. The x it's alone here, so we could do that. And this from 0 to L, we need to evaluate that. So remember that we need to evaluate the upper limit, the function in the upper limit minus the function in the lower limit. In this case, that is 0. So evaluate it in L should be L minus d Neperian logarithm of d plus L. And for 0, we will have 0 in here, minus, so that is plus d logarithm of d. And we are left with this expression. We can rearrange this a little further. We can use the fact that we can write this as follows, using properties of the logarithm. We can write this as the logarithm of d plus L over d. Yeah, so we can write this like this. And so we have found the electric potential. So we have all of this information. We have the value of the constant C, the length of the rod, which is L. We also have the distance to the point where we want to measure the electric potential, which is D. So we just need to simply substitute all of these values. So it will be this in here has a value of 9 times 10 to the 9th newtons per meter square over c squared. And the value of the constant c has a value of 28.9 pico. Pico is 28.9 times 10 to the minus 12, that's pico, minus 12 coulomb, let me verify, coulomb per meter square. And we also have, oh, this is it. And for the product in the brackets, we have the length, which is 12 centimeters. We can write that 12 centimeters in meters. So that will be 0.12 meters. We just need to simply divide 12 over 100 meters. That's the transform, or the converter factor. And in this we will have, okay, I said 0.12 meters minus the distance d, which in this case is, let me search for it, is 3 centimeters. 3 centimeters, so that this will be 0.03 meters. Again, we need to divide that by 100 and will be 0.03 meters. And the logarithm, as you can see in here, we can divide this and we'll have 1 plus the ratio between the length and L and D. So we will have 1 plus the length, which is 0.12 centimeters over, meters over 0.03 meters. When we put all of this into the calculator, we obtain a value of 0.001863 volts. So this is the electric potential at the point P1 from the rod. And this is it for this problem.